Dion is going to be showing us BASO4, Framework for Data Analysis, a plugin for IDA. So warm round of applause, please.
All right. How's everyone doing? It's cold out. Does anyone want me to do the other talk instead? I can do the black hat talk. No? All right. Damn you guys. Okay, so this is BASO4, barium sulfate. Does anyone know what barium sulfate is? Hands up. It's, no. Yeah, that's it. So it's radio. It shows up in the pictures when they take x-rays. So they give it to you either as an enema or you take it through the mouth. And then you get that. So that's a cat with a barium enema. It shows what problems are like inside with the intestines or leaks or any bad things. So there's a little bit of a metaphor there. Can anyone guess? All right. So I'm Dion. I write programs for a living. I'm a programmer. I don't really do this hacking stuff for money yet. And I write a lot of code. So I kind of get ideas about how the code will be organized in the commercial programs that I look at. And one thing that I'm always really looking for are new tools to understand those programs better, because C++ is really a pain in the ass to reverse. I don't know if anyone else realizes that. Static tools are just not good enough right now. We need dynamic tools to help us out. And this is a work-in-progress tool. I submitted it as a work-in-progress talk. The tool's not done. I'll show you what I have so far, and it's really a collection of tools. So I'm going to release the code after the presentation, and you guys can play with it and send me bug reports or feature requests or, hey, you're an idiot. The number one thing is finding bugs is awesome. I have a lot of fun doing it. I don't know why you're here or why you do it, but that's sort of the focus of the talk and the focus of the tool. Helping you understand the code to be able to find bugs and find logic errors. Yeah. So here's how I go about finding bugs. I go and read the PDF specification, and I say, hey, wow, this little bit here is probably never used by anyone outside of Adobe, and anyone that generates PDFs isn't generating them with anything but the Adobe tool for this little tiny section of the PDF. And I say, you know, I bet they made a few errors in the parsing of this or in the handling of how they're going to display this. So that's step one and step two. And then early on in my career, I would fuzz. So after that, I just throw things at it, find a sample PDF that had that, and just mutate it until bad things happen. But what I learned after about 4 or 5 months of doing this is all your fuzzers suck. They're going to go into one area. You're going to try and make them better. You might try and do some, even with some feedback fuzzing, you're not going to hit the corners, and you're not going to be able to do the thing that a human could do looking at the code. I think we can agree on that. So what's a better way to go about it? You want to audit the code that actually processes these wacky formats that they have. I'm picking on PDF, but obviously that's not the only thing. There's a lot of file formats that get parsed. And so the goal here is to be able to reverse the code enough that you can actually audit the bits that you're interested in without having to audit the entire big application, because that's a lot. So we have stuff that, it's easy to find the specification most of the time, or you can go, if it's not open, you can probably find it online. Someone's probably already reversed on the wire format, right? Not all the time, but if they haven't, then that's not something I'm really interested in. And then finding the dirty corners. Well, I don't know if anyone's seen my blog entry or has been in the business for more than a year, but differential reversing, where you run multiple inputs through a program and look at the coverage, and then you can diff the coverage and find out what the difference in the inputs were on the coverage. So finding places in the program that process just the part of the format you're interested in. People have been doing this for a long time. So Pedro Amini is always yelling that his process stalker has done this forever with the PyMay, and his is really fast. And then the guys at Dynamics do this now. They just had a blog post. They have some stuff to do it. And then number 3 is what we're going to talk about today, trying to find the code and understand it so we can audit it with some meaning. So the goal. I want a tool to tell me what part of the program processes what part of the input. And I want to understand it not just on the byte level, but more on the logical level. So if I'm parsing HTML, I want to know that, okay, who processes the blink tag? Because I want to kill that, right? So we want to go there, find out which part of the binary actually processes the blink tag, which one parses it, which one uses that parsed data that gets put somewhere, some logical abstract syntax tree, who uses that later to display it. Yeah. And here's the screenshot of the tool so far. So this is IDA, if you haven't seen IDA before. And on the right side is the current version of the way it's displayed. So that's sort of like an abstract syntax tree. And what this is showing is part of Adobe Flash Player parsing the AMF format, which is the serialization over the wire format for remoting stuff that they do. It's a good subformat to play with because it's specified in the document and it's easy to find. So yeah, that's sort of what we'll see at the end today, and that's where we're headed. And this isn't a new concept. I'm not representing it as such. I just haven't seen anything public that actually does it. Peter Banya has the SpiderPig that does very similar stuff, but as far as I know, that's not public. He released a demo and a paper, a really long, really in-depth paper about how he goes about doing the taint tracing, the taint propagation, which is data flow analysis, which we'll get to. But I'm pretty sure the code's not available. So what is BASO4? It's really a collection of tools. We have a fine-grained execution trace collector, which is a bunch of words. It just means record everything that you see that happens. We also have this control dependence analysis, which is a static analysis to find the basic blocks that determine, well, we'll get to it. And then 3 is taint propagation analysis. So taint propagation analysis is just tracking the input through the program, how it moves and where it gets stored along the way. And that's what we're going to use to color our color executable, those 2 and 3 together. And then 4 is the IDA plugin, which is just taking that taint information that we've captured in 2 and 3 and making it available to the auditor. So now we're going to, the whole thing is basically just a demo. We'll go to the slides back and forth between the demo and the slides so we can talk about stuff. But I'm just going to walk through the current use of the tool because that's really easy. Any questions so far? I haven't really said all that much, but all right. So the first thing we'll do is we'll look at this. Well, actually, let's talk about the first part, the execution trace. So what I call the execution trace capture tool is voidness. You feed it a command line, the address of the start function, so which module you want to start tracing, and the offset into that module, and a watch point set, which is optional, but this allows you to extend your trace. So you can say, every time I hit this line, I want to capture these variables, or this memory or this register, and this much memory. And at the end, we're going to have this trace that we can use for post-processing. Some tools will do the taint analysis, like taint check, for example, which is something out of I guess Berkeley with Donsong. Taint check does it all in process. So it uses a dynamic binary instrumentation to do the taint propagation while the program's running. They have to do it that way because the goal of taint check was to stop badness. So if someone's trying to use a tainted value as a function pointer, it would nuke it. But for us, we're going to take a whole trace first, and then we're going to post-process that. It makes it a lot easier to debug and reproduce your results, and there's a lot of good things that you get out of just post-processing and trace. So trace collection. You want to execute the program and record process state after each executed instruction. So you want to record everything you can to be able to completely replay the program. That includes registers, debugging events like exceptions, and where the modules are loaded, things like that. The naive way is to just record all the registers and any access memory after each instruction. That's, I mean, just thinking about it makes you cringe. How much would you be spitting to disk doing that? How much time would you spend doing I/O? Now, the guys at MSR came up with, they wrote a really good paper on this. It was the Nirvana project. So they have this reversible debugger. I mean, I guess GDB has something that does this now, but not the same way. The Nirvana project will take an entire trace of a program, and then they have these plugins that allow you to go backwards and forward in the trace to do a debug or to do, I mean, you could write BASO4 on top of that, but it's also good for debugging. So they described their method for doing this. And they maintain a whole shadow copy of memory and registers, and they actually emulate most of the integer instructions along the way. And then before they decide whether or not they're going to write out the new modified registers, the new modified memory, they match it against their shadow copy, which they keep by emulation. So they really reduce how much they write out the disk. Obviously, things can change, like memory can change in another thread, or your emulation could be not perfect, or it could be floating point, which they didn't do. And they also have these like checkpoint points, where they'll stop after every 1,000 instructions or so, and say, okay, here's all the registers that we have now. Make sure that everything you have matches this. If it doesn't, resync. So the other question, besides just spitting a bunch of things to memory, is how fast is this going to be? Well, obviously it's going to be slow. It's going to be really slow. But depending on how you do it will dictate how slow it is. Idea number one, the simplest thing you can think of is actually attach a debugger in single step. And that's what Ali debug run trace will do. Or I guess, I don't know if it still does that. That's the way it used to do it. I think in 2.0 it actually does something a little smarter. But that's not good. You can't run an interactive program like that with any reality. Idea number two is to modify a system simulator like QEMU to dump trace information. And this is exactly what BitBlaze, which is the Berkeley guys, that's how they record traces. And their tool is called TEMU. You should check it out. It's pretty neat. Idea number three is this dynamic binary instrumentation I was talking about. So dynamic binary instrumentation, in case you're not sure, it's really cool. It's like an x86 to x86 just-in-time compiler that allows you to modify the code as it's going through the compiler. So you can instrument, as each basic block is about to be executed, you get to pass it through, well, not executed. So it'll start out and you'll get a basic block. And if you haven't seen this basic block before, it'll get passed through an instrumentation function that'll allow you to add things like, record that this basic block was hit, for example, for a coverage tool. And then it'll cache that new instrumented basic block to the side. And anytime it hits that block again, it'll execute that without having to redo the instrumentation. You should check out the Dynamo tool. Where is it? Yeah, so the Dynamo paper from HP is awesome. It's a really good paper, and it explains it all in excruciating detail, but it really answers all your questions, and I think it was written really well. It's really cool. So DBI is used by Dan Reynolds' Trace Surfer, who also just takes a whole trace of stuff. His is for virus unpacking, things like that. So Voidness is implemented as a pin tool, which is this DBI. And pin is the Intel DBI tool. Other ones you might have heard of are Dynamo RIO and Valgrind. Valgrind is still, I think, Unix only. So other things about Voidness, other features. I was talking about those custom watch points. This is how we end up implementing the start to the taint. So while we're tracing the data flow through the program, we need to initialize we need to have some origin for saying that something is tainted or is an input value. So instead of using like read or send, or I'm sorry, read or receive or scanf or something that takes input from the system, you can actually do it on a watch point. So you can do it in the middle of a function. So if you know something's already been processed, unencrypted or decompressed,